All right, welcome to class today. It might be a little too close to the mic. Okay, I'm talking too loud. So today we're going to continue talking about point pattern analysis and talk about area pattern analysis. Specifically, I titled this lecture in Canvas as like pattern analysis and spatial autocorrelation. And this lecture, and to a smaller degree last lecture, are actually, we started noticing that this course GHY 715, which is a graduate-only course, and this course shared a lot of similarities. And so in the future, we're thinking about ways to kind of like blend the two courses. But I think, you know, I don't know if Ashley's sitting down there yet. Is Ashley down there? Anyway, but yeah, and so this course, anyway, this lecture is the only one that's like almost a 100% ripoff of a lecture in 715. So if you're going to take that next semester, then you'll notice. But there's some slight variations just because there's not the same level of detail in the back. So we did introduce these concepts before, but here we're going to show how they could relate to both. They could relate to both. Hey, Elvis. They can relate to both points and patterns. So we've got an example of a clustered point pattern and a clustered area pattern, and a dispersed area pattern. I mean, yeah, and a dispersed area pattern and a dispersed point pattern. Okay. Really, and then the final one with random, with the measurement that we came up with last week, which was the average nearest neighbor distance. Remember, we talked about how that's created. So in each of these cases, we have the average distance to its nearest neighbor. We add all those up and figure out what the average distance is, and then we divide that by the study area, which would be this like bean-shaped thing. And so you can see how the average distance to a nearest neighbor would be changed based on these three different types of measurements, right? I think it's a little bit tricky with areas. You know, if they touch, we could say, well, what do they touch? Do they only touch in certain places, or do they touch sometimes and not touch other times? So we're going to come up with a few other ways to quantify autocorrelation, spatial autocorrelation, besides just the distance. So we got clustered, dispersed. I already gave some examples last week, but there's some more in the lecture here if you want to read through them.
So, Dr. Rainbow, will you always be able to just eyeball it and know it's a clustered, dispersed, or random? We can look at it now based on spatial pattern, right?
Well, I mean, that's kind of the reason that we're doing the statistics. We're talking about ways to quantify it because sometimes it is hard to eyeball it and say that's definitely dispersed or that's definitely clustered.
Right.
More often, what we're doing this in the framework of a hypothesis test, and I'll talk about that when we get into the examples. But that's a lot what we do in that 715 course is kind of talk about the statistics. But more often than not, we're really comparing these things to random because it is perhaps maybe easy to see that it could be clustered or it could be dispersed. But is it likely that it's just a random pattern? In other words, the question we're really asking is the pattern that we see the result of some spatial process that created it, or is it totally random? Is there no self interaction with this variable, so that it did not create did not have any effect. In other words, one observation doesn't really have any effect on the other observation, where it will be in its location in space. Because what we're implying here is if it's clustered, then this thing tends to, there's a spatial process that explains why this thing tends to co-locate with other things of the same type. If it's dispersed, for example, last week we talked about central place theory, then what we're saying is there's a spatial process that tells us that thing develops in locations that are far enough away from other things of the same type. And finally, if it's random, that means that there's no dominant trend. It just occurs in space. So one of the examples I have here is lightning strikes. Just because one lightning strike happens in one location doesn't mean, and obviously there's a scale dependency here, but doesn't mean that a lightning strike will occur next to that one, but it could. They occur at random within areas that already see thunderstorms. If we just made a map of all the lightning strikes in the United States, and we use that whole area as our study area, we'd likely see some clustering. But that clustering is more about the fact that thunderstorms only exist in some places and they don't exist in others. Well, they're very rare in other places, right?
So thunderstorms could be random or not random.
Yeah. Well, the hypothesis, first we have to establish a study area and a scale of analysis for any geographic problem. So in the southeast, remember with tornadoes, we found an area with tornadoes that they were pretty random, but we had to like cut out just an area in the southeast. Same with thunderstorms. If we made a map of all the thunderstorms in the United States, there'd be some areas where there was less frequency of thunderstorms. Yep.
Is that because certain things do cause tornadoes to happen in certain seasons? So that's why you say that because that geographical area, it has a random pattern of always setting up like this. Now there's something happening unusual being able to change.
Yeah, I mean, if at one scale of analysis there's clustering, and there isn't at another scale of analysis, yeah, what that tells me is that usually there's not clustering at the finer scale of analysis. It's more random. Then there's no geographic variable at that scale of analysis that is causing a process that would cause clustering. All right, so actually, I think I'm going to go to here because one thing that's important to understand, this is slide number 7, is that spatial autocorrelation really starts with an understanding of what correlation is as a mathematical principle, right? So does everybody here know what a scatter plot is? It's that plot on the left, bottom left, okay? So it's just a simple, you can put on the scatter plot values, and each one represents a data point. So think of it as a row in a table. Okay, and then the x and the y would be two different variables. So it could be height and weight. You know, as you get taller, generally you get heavier, right? But there's some variability. If this is height here, there are tall people that also weigh a lot, but there might also be tall people that don't. I'm sorry, that'd still be tall. Tall people that don't weigh as much. Not me. I'm tall or tallish, and I weigh a fair bit, so I'm probably pretty close to the trend, right? So everybody's individual height and weight are mapped here onto this graph, and you get height and weight. That's what correlation is. And the closer that they fall to if all the points are clustered about a line, we refer to it as having a high degree of correlation. Okay, there's actually a mathematical number that represents correlation, the correlation coefficient. That just means that those two variables co-vary in space. So as one changes, the other one usually changes. So height and weight, they don't have a perfect correlation, but just because of the way bodies work, they have some degree of correlation. Yeah.
So that blue line is just your center line for standard deviation on the graph.
Yeah. So the blue line is the mathematical line of least. So it minimizes the distances of all the points to the line. It's the best fit, the line of best fit through that point, through all those points, through the point cloud.
Is that the same as standard deviation?
Well, standard deviation would be is a measure of spread. Okay, so the formula for the correlation coefficient is actually very similar to the formula for standard deviation. So the correlation coefficient, the one that tells us how close everything is to that line or how far spread apart. So if all of the points are spread far apart, correlation coefficient always ranges from 0 to 1. Okay? So if the points are spread apart, then you get something close to 0, meaning they don't covary at all. They're random. If all the points would line up perfectly on a line, it would be 1. Okay? Meaning that it's a they fit perfectly along the line. So the formula for standard deviation, anybody know what that is? Not the whole formula, but how do I calculate standard deviation? That number.
You got to get your mean first, right?
You get your mean.
You do like the square and then subtract it from
Right.
the mean difference.
Yeah, it's the average squared difference, the square root of the average squared difference from the mean. So you take all of the individual observations, subtract them from the mean, and square those, add them all up, divide by the number, and then take the square root. Okay, that's how you get the standard deviation. Well, the formula for this correlation coefficient, once the line, very few people nowadays will calculate this by hand because it exists everywhere, but if you think of this line as the line of best fit, it's kind of like the average trend that's occurring, right? So through space, this is the average trend that's occurring. And if I take all these differences from the average trend, those are called the residuals. And I can take all the residuals, find every single residual value, square it, and then add them all up, divide by the number, and take the square root. And that's pretty much how you find the correlation coefficient. Okay. So that's how that's done. But even a tool like Microsoft Excel nowadays will calculate the correlation coefficient for you. And that is something that we do want to move that down into this course eventually. But that's something that we talk about more in 715 now. Okay, so that's correlation. That's how we actually measure correlation. It's a measure of correlation. But in general, correlation can just mean do two values vary with each other. Okay, so we always hear about smoking and life expectancy. Okay, so some people might study that, try to find out how many years do they smoke, what's their life expectancy. We're working in attics. There's lots of insulation in life expectancy.
So we add auto to it, and that That's right. Doing the correlation, autocorrelation. When you add the auto to it.
Okay, so the auto correlation auto is the auto is with a variable that I should look up the exact definition here, but when two variables are correlated, they're unrelated to each other. Here we're looking at how this variable is correlated with itself, which is the auto part, and then the variable that it's correlated with itself and space. That's what we mean by spatial autocorrelation. All right. Go back here to this is I think where I left off. So that's this one. There's different ways to measure and define spatial autocorrelation. Some of them are fairly qualitative. We talked about Tober's first law of geography. That'd be a qualitative definition of spatial autocorrelation. Okay. And then we could measure similarity, the degree to which things are similar to other things nearby. That's moving away from being purely qualitative to looking at how different or similar they are. Not necessarily quantifying those numerically, though. And then these last two are what we're going to talk about today. More a little bit onto the using correlation. We're going to touch on this a little bit. Okay.
Dr. Rainbow,
Yeah.
they said that spatial autocorrelation in GIS helps understand the degree to which one object is similar to other nearby objects.
Yes.
So it's what you, that's what you're saying.
Yep. So here, so the auto, like I said, self, spatial, having to do with space. So if you can map it, it's spatial. And then correlation, degree of relative similarity. So you've seen these kind of graphs before, but here we've got positive spatial autocorrelation. Similar values are clustered together. And then negative spatial autocorrelation means that they're patterned and they're not clustered close together. They're evenly dispersed on the landscape in a pattern. So this is referred to as negative spatial autocorrelation. In other words, dissimilar values clustered together on a map. But when we're talking about self, we're talking about a single value. So we're talking about, if population did this, or if population did this. That's the two different types of autocorrelation. And in the real world, there does tend to be some randomness associated with it, or some unexplained. Sometimes a better way to say that is unexplained. Some unexplained thing that you can't see a pattern, but you can kind of see a pattern, and that's why we want to quantify it. That's why we come up with the numbers like this. So now we're going to talk about how to quantify that. All right? So let's talk about what's actually in this graph, because this graph is about graphing spatial autocorrelation. So what this graph is a graph of, because you guys can't see the x and the y, they just say y and yw. I'm not even really sure what that means. But this is every single pair of neighboring polygons. So this is the what do these neighboring polygons represent? They're enumeration units in Puerto Rico. I'm not sure actually what they refer to them as. It's probably a Spanish word anyway. But so these are enumeration things. Think of them like counties maybe in Puerto Rico. Okay, so that's Puerto Rico. And then this is the population density is known for each of these counties in Puerto Rico, or each of these enumeration units. And so every single pair of touching counties is in this scatter plot. So like these two counties right here, this one has a moderate value. By the way, the reds are high, greens are lows, whites in between. So these two pairs right here, this one and this one, there's a moderately high value paired next to a high value. So that would be moderately high value next to a high value. That could be that one right there. I'm just guessing. It's probably more like one of these. Because there are several. Actually, I don't know over here. I don't know which ones correspond with which one, but the scatter plot is every single pair. So if there are, I don't know, 100 units, it's every single pair of units that touch each other. So there's no way to like predict exactly how many there's going to be until you actually have the marks, because this unit right here doesn't touch that unit, right? So that's not on the chart. But this one touches that one, so that's on the chart somewhere. All right, so this is population density. And this is demonstrating positive spatial autocorrelation. Correlation in general that's positive, the line is trending upward. In other words, as one increases, the other increases. So what this is saying is, as my population value increases, my neighbor's population values increase. That's what this chart is showing. So high values are surrounded by nearby high values. That's what that's saying. And also, low values are surrounded by other low values, and intermediate values are surrounded by intermediate values. Are there exceptions? Yes. I pointed one out earlier. But for the most part, there's a trend. That's what this is. So the trend, the correlation coefficient, is going to tell you how strong that relationship is. And in space, it's never going to be perfect because we actually have to have, just because of the way space is, there has to be a boundary between the highs and the lows somewhere, right? And so you're going to have a trend like this. So this is positive spatial autocorrelation. So here's an example of negative spatial autocorrelation. So now you can kind of see how when the GIS software does what it does, you can kind of see how it's doing it, right? So it's building this kind of chart, and here we've got negative spatial autocorrelation. In other words, the trend is going down. In this case, it's grocery store density. So high values are surrounded by nearby low values. What does that mean with grocery store density? In other words, first of all, what does a high value mean here? Grocery store density.
It means how many grocery stores in that particular plot of land.
Right. There's how many grocery stores in that enumeration unit. Okay. And so I'm not sure in this case whether it's been normalized by people, but it really doesn't matter. So yeah, high value means there's lots of grocery stores. Green means there's not a lot of grocery stores, and white means that it's in the middle. It's moderate. And so
it's kind of trended toward the middle portion of that area of Puerto Rico. It's like all the high areas trend toward the middle. Looks like.
Yeah, I mean, like you're saying, the spatial location is that there's a core of grocery stores in the center, and then around the outside, there's less grocery stores. Right. And I don't know. I've actually never been to Puerto Rico. Well, I've connected to the airport like 5 or 6 times, but I've never been off. I've never been out of the airport, but you know, I can imagine a scenario where the beachfront property has less grocery stores than the hinterland. I don't know though, but that's definitely what this is mapping, right? And is it as strong as the population density? Well, the strength of that relationship is determined not by the slope of the line, but by the spread here. I mean, the slope actually has something to do with it, because if the slope is totally flat, then it also means that there's really nothing, like one isn't affecting the other. That just means that one of the two variables doesn't change at all.
So when the trend be toward the northeast of the island of Puerto Rico, we're just looking at it on the scale of the northeast.
We're not really looking at the location of the trend right now. What we're looking at here is due do high values tend to be closer to low values, moderate values, or other high values? In this case, the trend in a dispersed scenario is that they tend to be, high values tend to be clustered next to low values. That's what this is saying. High values are surrounded by nearby low values. Intermediate values are surrounded by nearby intermediate values. And low values are surrounded by nearby high values. So why could that be? What could be the spatial process that explains this scenario here? Or this pattern on the landscape?
All the people in areas without grocery stores, they just go like to the section over to go to grocery stores.
Right.
Like,
yeah, people can travel to a grocery store. That's true.
you have like residential areas and commercial areas.
Yeah. So land patterns tend to like make it so that there's not a grocery store like every 20 feet, right? There's commercial areas, and they're dispersed on the landscape, and they don't co-locate. Grocery stores don't co-locate right next to each other, because then they would be in direct competition with each other, and eventually one would die, right?
Out in the hinterlands, you could have lots of small population centers, each with their own little grocery store.
That's a great point. So I don't know if you all heard that on the coast, but up here the comment was made that here in this center section, where you see a lot of grocery stores, you could have lots of little grocery stores, whereas here in urban areas you might have one or two grocery stores, and people or travel longer distances. Maybe there's more access to public transportation and whatnot that causes that. But that'd be something to investigate. Again, just like I said last week, what I'm teaching in this is not necessarily about grocery store. Well, it's not about grocery stores, but it's about using these tools for whatever you're interested in. And I don't understand all of the reasons for the pattern that exists in this case, but it's a tool to study patterns.
Also, if there's a larger area, I don't think that the correlation of what we're making out the grocery store would fit that pattern, because it's so small area, it's almost an oversaturation of grocery stores. So because the area is so tiny, everybody got moms and pop stores.
Yeah.
The density is very high.
A lot of Dollar Generals do Walmarts.
Right. Yeah, Dollar Generals here are a good example. All right. So now, sure. Yeah. So before I move on too far, there are different ways to define. Like I just said, this graph shows everybody compared to their neighbor. Okay? But we could decide that we wanted to quantify correlation, a spatial autocorrelation, and define what a neighbor is differently. We could say that it's all of those, all of the county or enumeration units that are within a certain distance. And we could even weight those differently. So there are different techniques that will actually allow you to say, well, we'll count this we'll count this doubly if it actually touches, but then if it's within 100 or 200, I don't know, meters, that's probably more than 200 meters. Maybe 2 or 3 kilometers, we'll still count it, but we won't weight it as much. All right. So we'll talk about that here. All right. So we've got these are kind of general things that we've already hit a bit. All right. So the degree to which characteristics of one location are similar to another. Similar to equals positive spatial autocorrelation. Different from is equal to negative spatial autocorrelation. So you can see why that math works by looking at these charts. Usually, it's easier to come up with positive spatial autocorrelations examples than it is negative autocorrelation examples. But they do exist. We talked about it several last week. Usually animal habitats where they're in direct competition with other animals of their same species tend to be like that. Grocery stores, large settlements on a plain with no other externalities affecting that area would also have that kind of spatial pattern where they exist, not in a clustered way. All right. So usually we're looking at a pattern and we're trying to decide, is it dispersed? Is it clustered? But the kind of the default assumption, the null hypothesis, if you will, is that the pattern is random. Okay. And one of the reasons that we calculate these measures of autocorrelation, spatial autocorrelation, is to determine if that pattern that we see could have been created by chance. In other words, is it truly a random pattern, or is it a clustered pattern? What's the probability of that pattern existing if it was created based on a random event? Because if the probability is very low that it was created on a random event, then that's interesting. There's something we could study. We could try to find out what the spatial process is. So that's what this is saying. Spatial autocorrelation is important because it implies that existence of a spatial process. In other words, if we can quantify that it's not random, that there's either a dispersed pattern or a clustered pattern, then we can start to make theories about or even further study, and we can use the spatial autocorrelation to support the existence of a spatial process. Okay.
Is a negative spatial negative spatial autocorrelation, is that only say that man has to do with it, or does it have to do with man or nature? Is negative.
I'm sorry.
Is negative spatial correlation, is that something man-made created, or just a pattern just negative, whether it's nature created or man-made? Is it generally associated with being man-made?
No, I mean, the example I gave about, like big predator habitats, they usually disperse across the landscape because they would be in competition with each other if they overlapped a lot. So there are both natural examples and human examples. But I mean, in reality, I think that the spatial processes that control these things are related. They're similar. Like, in other words, basically competition effects cause dispersion to occur, and then effects, I don't know, I can't think of a single word, but things that benefit from the sharing of resources cause positive spatial autocorrelation. So competition causes negative spatial autocorrelation, and sharing causes positive spatial autocorrelation.
Positive will be more closer together in a certain pattern, and the negative will be more spread out. The different things in that pattern.
Well, both random and dispersed can be spread out, but dispersed means that they're methodically spread out, that there's some process causing the spread to occur. Random means that they're just happening by chance anywhere in space. So they have their own, we're not going to get too far into statistical tests in this class, but they have their own inference tests, these measures of spatial autocorrelation. ArcGIS will run these for you. We've already shown it with the average nearest neighbor, but we'll demonstrate that as we run these with a few other times, and with a few other examples. All right, we already talked about just the raw scatter plot, but you'll see also when spatial autocorrelation is performed, they'll sometimes report this thing called a variogram. Now, this is a little bit different than the scatter plot that I showed here. The scatter plot I showed here, just each point represents a point pair that is assumed to have some relationship. So they're either the nearest 2 points or they're within a certain distance of the points. Okay, that's a little different than what we're showing here. The variogram is shows the relationship between all locations. So if we were to map the variogram of this, we'd have every single value, every single pair of values mapped. And the y-axis, the x-axis is the distance between the two observations. So distance is on the bottom. Okay. Whereas in this map, in this diagram, neither one of these is distance. They're both the value that we're mapping. So in this case, it's grocery store density. So this is grocery store density, and this is neighbor's grocery store density. Whereas in a variogram, this is the difference in the values. So in other words, the difference in grocery store density, and this is the distance between the geographic locations. So it's a different way to quantify spatial autocorrelation. So what usually happens is that this graph is more useful for telling you at what distance spatial autocorrelation breaks down and is no longer an important factor. Because if you think about it, let's just say I'm looking at a variable population density, right? So is the population density where I am related to the population density? Population density is kind of weird because it doesn't really exist, right? Like population density is a measure of an area unit. So anyway, let's do a different example. Rainfall. Is rainfall related? The rainfall right here, is it related to the rainfall 10 feet away from me? Typically, yes. In fact, they're almost always really, really similar, identical. And I'm not talking about the fact that I'm inside. I'm not going to get any rainfall right here, right? I'm talking about just the rainfall on this piece of Earth versus that piece of Earth. Now, as I go out, you'd expect it to be less related. Like, in other words, I could get 50 inches here and maybe 48 inches if I went a mile down the road. 2 miles down the road, I'd expect the values to be similar. 2 miles that way, 2 miles that way, 2 miles in every direction. I'd expect there to be some variability, right? But I would expect it to be pretty similar, but there'd be some variability, right? Now, what if all of a sudden I went to Nebraska? Would I expect the rainfall there, over time to be similar at all to the rainfall I received here? Maybe on some climate scale, I don't know, wet years in general there might also be wet. A wetter year in Mississippi might mean that it's also a wetter year in Nebraska, but not necessarily, right? And it would start to be totally different. Now, if I went all the way to China, we'd never expect those two values to be related at all, right? So that's what this graph is showing. This graph here that shows distance between your geographic observations in the X, and in the Y, it's showing the difference between the observations. So in other words, these points, I need to remember to stay over here so that this gets recorded. These points right here are really far away from each other compared to these points. And some of them are very different from each other, and some of them are not very different from each other. Okay? Well, at least they're not any different than points that are closer. So as you get up here, you have greater differences between the points. And as you get down here, you have less distant differences between the points. In reality, this is like idealized. In reality, you might see points that were like all of us, like after they get to a certain point, they're like spread all over, right? Because, the China example, somewhere in China, they received the exact same rainfall last year that we received here, right? So that would be like down here. They're really, really, it would be like way over here. They're really, really far away from each other, but they had the same value, right? So that is the variogram. So sometimes you'll see spatial autocorrelation output, and they'll show you the variogram, and sometimes they'll show you the correlation, the scatter plot. Right. All right, there's a couple things to take away from this variogram. The first one here, I'll just kind of go this way. The first one's a nugget. The nugget isn't really that significant, but what it tells you is that those are like the that tells you where it hits, where the y-axis basically hits distance. So you don't usually have any observations past a certain point, and so sometimes you don't know where this intercept occurs. Okay, that's what the nugget tells you. The range is really important. I'm sorry, not really important, but the range is a more important variable. The range tells you the point at which, and that's the point at which. Sorry, the range is the point at which this curve levels off. And what it means when it levels off is that there's no more correlation. In other words, the distance between geographic locations isn't causing the scatter plot in this case to turn at all. It's just level off. In other words, there's as many high values as there are low values. And what that means is that there's no spatial autocorrelation that occurs beyond that range. That's what's called range.
Is it possible, Dr. Ray, if, let's say we were looking at an area in a mountain range, starting at that location would knock off the pairs from being bonded together? Could the environmental conditions cause those patterns to change?
Oh, certainly. Yeah, all sorts of things could cause this to change. So this is interesting to look at because you can say, let's say this was 10 miles. No autocorrelation exists after 10 miles in this area. What that means is that for whatever variable you're mapping, there's no effect from that variable to another unit that is measurable past 10 miles. So they're not related. They're not influencing each other beyond. They're not influencing each other's values beyond 10 miles away. So if this was rainfall, for example, if this was graphing rain, this is a variogram of rainfall. What it means is that the rainfall is the rain clouds that are happening in the area are usually smaller than 10 miles. Okay, they're just dropping their load right there, and we can predict the value that is happening within 10 miles. But once we get further than 10 miles, they are not going to get rainfall related to that rain event. We could use this to measure like let's say we were in an elevation, like we could use, like you're saying, a mountain. If we had a mountain and the mountain, we were at the top of a mountain, and we measured all around the mountain to do spatial autocorrelation, and we made a variogram of that. We'd expect to see that drop off as we got away from the mountain, and there started to be other things, other mountains, smaller mountains, the undulating landscape. That would be over in this area. So you can actually see different patterns. This line of best fit, you can also specify how you want to model that line of best fit sometimes. But anyway, the range and the sill can be interpreted as the, so this is the average distance of value. So the maximum difference in value at that range. So if this was precipitation, that would be, let's just say this was, this started off at 0, so this might go to 50 inches. Okay, so the sill would be 50 inches. And what we'll be saying is any difference over 50 inches is not usually measurable to influence other points or other locations.
So you say there will be no correlation between those outlying points?
Right, these points, there's no correlation. See, they just scatter about the line. Here, the points are closer to one another, and there's actually like a line, in this case an arc, that we can fit in between them. So oftentimes when we go to measure spatial autocorrelation and come up with are these things related, we could look at the variogram first, and then once we look at the variogram, we could use that to measure the to determine what near is, because in some of these measures of spatial autocorrelation, we need to specify what a neighbor is. So with points, it always has to be a distance, what a neighbor is, right? Because they don't actually touch each other. We could say the nearest one would be its neighbor, or we could say that all of the points within a certain distance are their neighbors, or in this case, we could say that they're next to other. If they're polygons, we can say, are they next to other polygons? Right? So there's a few different ways to do that. So there's basically two different ways for coming up with these. So far, the examples that I've given, the measure of nearness is binary. In other words, you're either near or you're not near for measuring spatial autocorrelation purposes. So if we're going to include you on the scatter plot, you're either in or you're out. Okay? So you're touching or you're not. That's what weights based on contiguity or binary weights means. So if zone J, enumeration unit, census district, plot, if we're doing some environmental work or
It's kind of like pass fail, you're in it or not.
Yeah, you're in it or you're not. It receives a weight of 1 or 0. So it's essentially excluded if you don't say it. All right. So we still want to. Okay. We can still base this on distance, is what I'm trying to get at here. Contiguity can still be based on distance. In other words, we could define a neighbor as only those values that are touching each other, but we could also define a neighborhood as being all of those values within a certain distance, but we could weight them all equally, right? However, we could also base them on distance and then set the weights on some continuous variable. So they could measure the actual distance between points, between polygon centroids, and usually what we do is weight them inverse to distance. In other words, as you get further away, they have less of a weight. So in the scatter plot, they're, I gave the example before, you could double count or triple count it, but you could also count it as 2.5 of a value rather than 1 of a value. So you can multiply it by the weight.
Does a buffer tube, does a neighborhood tube work within a buffer itself? So you might want a certain distance around a certain area, then you want to have a neighborhood inside that buffer. Does that help in narrowing what you're looking for using a buffer tube?
Yeah. So a lot of this in the past, when GIS was first developing, you would have to calculate a lot of these values by hand. And so I think the question you're asking is basically, how do I do this? Do I do a near tool and then a buffer? Like, how do I figure this out? Well, nowadays, I'll just go ahead and open up ArcGIS. Nowadays, when I go to calculate these autocorrelation numbers, which we haven't actually quite gotten to, but we will in a second here. All right, so here's just an example. I downloaded the week 7 data again. That's what I'm going to use as some data. So I'm going to add some data and do these county health rankings. Okay, so these are county health rankings, and there are a number of tools. Let me open up the toolboxes. They're all under the spatial statistics tools, and we talked about a few of these last week. The average nearest neighbor. We're going to talk about a few of these in just a second. So, so here is spatial autocorrelation, the simplest one. This is, although we haven't yet talked about what this means, this is a global measure of autocorrelation for the entire data set. In other words, it's going to, in the background, it's going to be creating a scatter plot like this, and it's going to come up with a single number for that scatter plot. Okay, and this is what we're talking about here. So I guess the point is, you could just press a button, but how do we establish these spatial relationships? Do we use the near tools, the buffer tools? No, they're just built into these tools nowadays, where you can say, I want to conceptualize the spatial relationships using, as I said, inverse distance. In other words, do I want to weight nearby points more than far away points? Or do I just want to say only those that touch each other will be considered neighbors for the purpose of creating spatial autocorrelation? That's what that is. In other words, contiguity with edges only. So in all cases, I have to choose which data set I'm going to use, and then I select an input field. Here we might just do percent obese here. Okay, sure I fall into that category. All right, so then I could just say I'm going to look at all of the pairs of counties to determine, is spatial autocorrelation going on? In other words, are counties that tend to have obese people next to other counties that tend to have obese people, or are they not related? In other words, are there obese people everywhere, kind of just spread into the population as a whole? So some counties are obese, some counties aren't, but there's no spatial pattern to it. What do y'all think?
About what?
Which one? Do you think that they're random, spread out in space in the United States?
No.
Or do you think that
It's clustered in certain areas.
clustered in certain areas, right?
I question too, based on how we got these stores and
So here's this is by county. So these are county data. So I'm going to run this guy, and if I do edges only, in other words, I'm only counting pairs, I'm only building my scatter plot with neighboring values, next door values, then I'm going to get this this output. Now, this is just telling me that that there are a few counties in the United States, I guess, that that had no neighbors. I don't know where those are. Maybe they're Hawaiian counties. Anyway, so I don't. I'm just going to ignore the warnings because I don't really matter. But so here's the map. I mean, sorry, not the map. This one actually doesn't produce a map because this is just telling you for all of your data, I'm going to build a scatter plot, and here's the result of that. Okay. So Moran's index, which we'll talk about in a second, is basically the correlation coefficient. So is that value, positive or negative? It's positive. So before when I said it ranges from 0 to 1, I meant -1 to positive. So this is positive. So it's positive spatial autocorrelation. What does that mean? Clustered, yeah. It's clustered. So in other words, counties that have obese people tend to be close to counties that that have obese people, and counties that aren't obese tend to be close to counties that aren't obese. Yeah. None of that. It's really strong. Yeah, go ahead.
were we correct in saying that they're probably more custom together?
Yes. Now let's see how the numbers change. I'm just curious. If I said, inverse distance squared, I'll just go straight up inverse distance because it'll be more. Inverse distance squared tends to say it basically weights closer counties even higher than further away counties. So inverse distance squared means that it's the inverse distance, but it's squaring that value. So it's even further weighting close counties. I don't expect this to be that much different. And there's probably a lot of variables where this is the case. But there could be some that aren't. So yeah, it's pretty similar. Okay. What was it before? 0.4 versus, it is higher, but both of them are very significant, statistically significant. Okay. All right. Both very, very positive. But it did change it a little bit to use inverse distance weighting. There may be some where it has more of an effect. Okay. You might especially see it more with dispersed. Because dispersed, sometimes it really is a pattern like, it really is a pattern that looks something like this, then it really is just neighbors, right? And so you might see a stronger negative spatial autocorrelation if you just did neighbors rather than doing everybody.
Was it supposed to produce a output on the map?
No, neither one of these. This is basically just the equivalent of this. It's just telling you the slope of this line for you, and it's telling you how significant it is that it's not a random pattern. So in other words, obesity in the United States is definitely not, it's not distributed randomly across the landscape. Definitely clustered. Right. We could make a map of it, just a straight up map of it if you wanted. You mean that's pretty easy.
Yeah. That would be interesting.
So we could just make a map, right? That'd probably be the first step anyway, not unique values. Graduated colors and percent obese. Right? So we should have done that first. We look at it. Is that clustered? dispersed, random.
This is
But we just ran the test on it and found out that it's definitely clustered. Yeah, what's that?
I said the density is it kind of based on reality is the density of obesity is tab is solid. For I'm missing there one of the highest obesity in the nation. And
Yeah, I don't know what the very highest point is, but there's also, here in Appalachia, the kind of like the low country, that's what we call it in South Carolina. I don't know if they call it that all the way through here, but.
California is no obesity.
Nope. Yeah. So I grew up there, but still kind of large. All right. You also got some pockets up here, but in general, you do see those patterns. Now, a few of the other, we're going to talk about a few these other tools that build off of this tool. Okay. But first, let's talk about. Let's see. So this is what we're talking about. Do they share? When we go into here, when we go to run it, whoops. When we go to run, it. If we did contiguity with edges only, contiguity with edges and corners, that's the difference between. Sometimes in other GIS software packages, sometimes I'll actually refer to it as like rook versus queen connectivity, and that's really derived from chess. Rook is the same as edges only. Queen is the same as edges and points. If you have hexagons, you're not going to have any points, like we did with the tornadoes. But lots of times, you're just dealing with irregular data. Okay, so the deciding on how you're going to do that, how you're going to determine what a neighbor is not like, sometimes it's just an experimental process, but sometimes you really need to think about the pattern that exists and the data that you're using. So, for example, that's what I said before. If you scroll up to that other one before, where the negative spatial autocorrelation. If you're trying to show negative spatial autocorrelation, it really matters. You do have different ways of actually measuring distance between things. Like, is it edge to edge? ESRI gives you all those. So here, if they're no, there's no edge to edge. I thought there was. What's that?
This always got to be when you're trying to find a relationship. This has always got to be a part of it.
Yeah. Well, distance doesn't always have to be part of it. It can be contiguity. That's what I'm trying to say here, is that there could be lots of difference. So what do you think fixed distance means? This fixed difference band means?
It would be in concentric circles.
Yeah, there's usually just one. Like here, fixed distance means you're allowed to enter one fixed distance. The distance is right here. You're allowed so everything within that distance is considered a neighbor. Zone of indifference. I'm not even exactly sure what that one means, but we could look it up. And then this last one is important. So getting back to your question, what this requires to get spatial weights from file is having a file with all of the pairs that you want to consider neighbors and the weight associated with that pair of neighbors using their FIDs. So we could, for example, run the near tool, and if we wanted to use some other derivative of distance, like we wanted to cube them instead of square them, inverse distance cube, we could come up with our own spatial weight from file. Or if we wanted to do the distance along, like let's say we had the river system of the United States, and we thought that obesity might be related to the distance along the rivers. I mean, that'd be crazy nowadays because rivers aren't the main way that we share a common cultural, like just because two people live on the Mississippi doesn't necessarily mean that they have the same tendency to be obese. But let's say it did, then we could weight their distance along a river network, or maybe even better, we could use network analysis, throw it on here, and weight things by the actual transportation distance away from each other. See what I'm saying? You do transportation distance, and you could use that to derive your spatial weights, and then you could take your spatial weights and feed them into autocorrelation and say, is there clustering that occurs along the this network corridor? So that'd be an interesting hypothesis to do. So you could also see if the clustering became more significant if you used the network distance versus the actual distance. You see what I'm saying?
Network distance would be distance you actually travel on.
Right. The network distance would be the distance that somebody would actually have to travel. So, yeah, if you look at this, it'll probably tell you the format of that file. I've done it before, but I've done it infrequently enough that I don't remember it, the format of that file. But yeah, so your weights matrix file, you give it an SWM extension, and then you can either generate it. You can use the generate spatial weight matrix tool, which will actually allow you to choose. So you build an attribute table and choose an attribute. Otherwise, it's expecting an ASCII formatted spatial weight matrix file where yeah, rows are standardized. Let's see, weights are used as is. Okay, so you just feed it the weights. So it's warning you that it's going to be memory intensive. Okay. So it's from to weight. All right. This is actually pretty. Do you remember the what would create this? Back in Network Analyst, we talked about network analysis. There was a tool we talked about in the lecture that if we throw in all of our origins and destinations, there's a tool. What's that?
What is the origin destination?
Yeah, the origin destination matrix is going to produce this. We're still going to have to like do some value to turn distance into weight, because it's distance is in the opposite direction. In other words, 0 distance should be the highest weight, and vice versa. So yeah, you create your origins and destination matrix, and then you decide how you're going to turn those weights, which ideally are scaled between 0 and 1. And so you rescale them. You can basically find out what the highest number is, and so you can divide everything by the largest number and then invert it so that zeros became 1 and 1 became 0. That's just a subtraction problem. All right, that was a little bit of a tangent, but I was showing you the analysis that could be done. All right, we talked about these last week. These are ways of doing spatial autocorrelation analysis. So point density, sometimes you have to aggregate to polygons in order to even start doing your spatial autocorrelation analysis. Sometimes it's just easier to see and explain patterns if you aggregate. Okay. All right. So we did nearest neighbor analysis last week. We did this last week, so we don't need to do that. All right. In fact, we even did this one last week, where we talked about the number of points per quadrant. Oh, this is a little bit different than than exactly what we did last week. So the average nearest neighbor point analysis is different than this is called quadrant analysis, and this looks at the variance mean ratio. It's a little bit more robust than just the average nearest neighbor. The way that it does it is it counts up the number of points in each quadrant, and you basically get a number that represents the number of points per quadrant, and then the expected number of points per quadrant. How would you get the expected number of points per quadrant?
Just an average.
Right. So you got your number of quadrants and your number of points, and if you divided them equally into each other. So if you have 300 points and you have 100 quadrants, the expected number of points per quadrant is 3. So that's what that is. Now the variance is taking each of these and subtracting them from the expected number of points per quadrant. So in this case, it'd be, whatever the expected number is minus 9. That's what this is. So the number per quadrant minus the expected number times 2 squared divided by the total. In this case, it's n minus 1. Usually statistics that use n minus 1. So what this boils down to is that in a random one, it's going to be close to 1. If it's totally random, you're going to get a value close to 1 for your mean variance ratio. If it's uniform, you're going to get a value close to 0. Why will you get a value close to 0? It's because all of your points will be very similar to the expected number of points. And then clustered, you're going to get a value higher, much higher than 1. Now this mean variance ratio, unless they've added it recently, that's not one of the tools in spatial, the spatial autocorrelation. The spatial statistics the spatial statistics toolbox. Yeah, I don't see it. That's the one we talked about last week. Yeah. But this is something you could do by hand. We've already done the first step. You take your points, you do a spatial join, and then you have the number of points per quadrant, and then you can figure out the average number of points by just taking the total number of points, dividing by the number of quadrants, and then you could calculate this by just taking the column in the join count column, right-clicking on that column, and calculating the variance for that column, or the standard deviation times 2. Standard deviation squared. And then taking the mean and dividing it by that number. All right. There is a hypothesis test for this analysis, and it involves using a chi-square test. But we're not really gonna cover it in this class. Okay, that is something we cover in 715 a little bit more. Okay, so this is just showing you how you could take the values and calculate that maybe.
How is that related to the statistics they have? In the statistics, how are you talking about that?
Yeah. We are going to talk about the statistical tests. Well, we already did talk about some of them, right? These guys. But I'm not going to do the calculations for the statistical test of the mean variance ratio. Okay. Now there are some disadvantages to using the quadrant analysis. One is that it really depends on what size you use as your quadrants. So if you think about this particular data set here, these would have the exact same value, these two right here. They would have the same value for the mean ratio, and therefore they would test the same, even though they look totally different. And you can argue that one's clustered and one's dispersed, even. So, so really, it's a measure of dispersion, not really pattern. And the same with the one we talked about last week, the average nearest neighbor distance. Okay. And then, of course, just like the one we've already talked about, the global Moran's eye, it results in just a single measure for the entire distribution. All right, this is the one we did talk about last week, average nearest neighbor. Again, this one is really sensitive to the study area, the size of the study area. Okay. So the area of region results vary dependent on this value. And I talked about this last week, but it is really important to use projected data. So just another thing. So you can notice that the data that I used, the data I used here is definitely projected. Need to have real distances measured. There is a statistical test for the average nearest neighbor, and we showed that last week. So when we ran it, we got a number, and that is the Z statistic. Remember when we ran it last week? We expected it has a normal frequency distribution. And so the Z test statistic tells us how many standard deviations away from the mean it is. And the area under a normal curve will tell us the degree to which we could consider it an unusual observation. So I'm going to show that here real quick. So that's what this is, right? So the Z score is the distance away from the mean, standardized distance away from the mean. And so if the Z-score is 1, that means it's 1 standard deviation away from the mean. Okay. If it's 2, it's 2 standard deviations away from the mean. Well, this is 79 standard deviations away from the mean. And this chart, in reality, this line would be so far over, you couldn't even really see it. Okay. So it's very significantly clustered. That's what we can say there. The area under the curve here, if we said that the total area under the curve is 1, then what we could do is say 1 minus that value, and that gives us the p-value. The p-value tells us the probability that that spatial pattern would be created by a random event, by a random spatial process. So in other words, a really, really low probability. It could happen. There's always a chance, but it's not really happening that often in real life. Like, in other words, the probability of that being created, in our case, the probability of this spatial pattern as a result of a random process is 0.00000. It's like non-existent, right? Now, statisticians will get in and tell you that this is either created by a random process or not, right? So technically, what you should be saying is that a spatial pattern like this could be created by a spatial process. I mean, by a random, at random is very, very low. There's less than 1% likelihood that this clustered pattern can be a result of random chance. That they stated the way I stated it. All right. Yeah, we're not gonna. So basically, the z value is a function of the is the distance values that you've created divided by the standard the standard deviation or the standard error. So that's how this is created. That's how that z statistic. So we're not going to, in this class, we're not going to worry how the z statistics comes to be, but that's the formula for it. Okay. All right.
Just say, it helps you explain by that map. It is not random.
Right. The higher the z-score is, the further away from the mean you are in standard distances.
So if the z-score was negative 79, what would that say?
That would say that the pattern was dispersed and with a large degree of confidence. Very confident that it's dispersed. Now, if it was like 1, it would be on the dispersed side, but we would only have 1 means that there's one standard deviation. I forgot. 1 standard deviation. How much under curve? I think it's 68%. 68%. So in other words, if it was 1 standard deviation away on this side, and then what that's saying is that this side has 68%, and this side then has 32% of the curve underneath it. So what we're doing is saying that that on average, that could be created, that clustered pattern could be created 38% of the time if it was random, which isn't safe enough to say that it's not random, because 38% of the time it could be created by a random chance, that pattern that you see on the landscape. So it's, you know, not good. And then you can decide where to make your cutoffs. This is showing you the 10, the 5, and the 1% cutoffs, and it's beyond the 1% cutoff. And these numbers are always going to be the same because it's standardized. So 1.96 is always the cutoff for 5% of the time, if it's a z-score, and these are all z-scores that we're talking about today. All right, so those are some examples of running the average nearest neighbor. Now, just to be clear, this analysis is not average nearest neighbor. We ran that last week. All right, so here's some advantages and disadvantages of the average nearest neighbor index, which I think, yeah, we already said. So there's no quadrant size problem, but it is it's heavily dependent on the size of the study area. And again, it's not looking specifically at pattern. It's looking more about distance. So it doesn't incorporate local variations or clustering scale. It's based on the point locations only. All right. So now let's look at areas. I'm gonna. No, I keep forgetting we've only been here for an hour and a half, so this is fine. Okay. Before we get into measuring some of these things, we're going to talk about a few just general properties of areas. Areas represent hard boundaries. They can also represent things that don't really have a certain boundary, like a wetland. So area objects are created using polygons. We all knew that. Often a polygon represents a single object. So sometimes there could be overlapping polygons. Typically in one layer, you don't want overlapping polygons, right? So whether that means that we're talking about, in this case, counties, right? You don't want overlapping counties. That doesn't even really exist. Counties, by definition, are a fabric. They exist only They exist everywhere, but they don't overlap. But even if it represented some, environmental variable or land cover, like let's say it represented wetlands, we don't want two wetland polygons overlapping each other in a single layer. If we do, then we could start to get errors when we go to run these autocorrelation tools. And usually they represent errors in real life. So somebody delineated a polygon and then somebody else delineated a polygon to represent wetland, and they didn't merge the two polygons, and they have overlapping areas. And so ArcGIS provides tools for what's called planar enforcement. Planar enforcement allows you to take polygons that are next to each other and create a single polygon, or if one polygon needs to be superseded into another polygon, that's fine too. So sometimes they're appropriate to do, like if we just wanted to merge, if they both represented wetlands and we wanted to push them into a single polygon and get rid of that overlapping area, we'd do a dissolve. Okay? I didn't want to ask the question because that seems like the right answer for a couple times last week. If they truly represented two different polygons, but we can't have them overlap, then we can do planar enforcement. All right. We can calculate the area of a polygon. We can calculate the center of a polygon. There actually are a few different ways to calculate the center of a polygon. One of those ways is to calculate the mean center, and it calculates the weighted average location of the entire polygon. Similar to with the points, but it uses mathematically, it finds every single location in that polygon and calculates the weighted average location. So if it's a horseshoe shape, the mean center is going to be where? Outside the polygon. Sometimes it's desirable, or lots of times it's desirable to have the center location inside of the feature, in which case the most popular or the most common way to do it is called the skeleton to center, where it slowly, not slowly, it doesn't do it slowly, it does it very quickly actually, it builds an interior buffer until there's only one location left and uses that as the center. If in the case if you have a very regular polygon, it is possible to have two centers, and it chooses the one that's closest to the mean center. But that's the skeleton to center. Increasing interior buffers. In other words, it's slowly buffering it until it finds the center. And I didn't mean to say slowly again. It does it very quickly. All right. There are measures of shape that we can use to quantify what a particular shape is, whether or not it's a long, skinny feature, or whether or not it's a circle. So one of the more common ones is the compactness. The perimeter area ratio is one measure of compactness, one common measure of compactness. And what this does is it takes the perimeter, divides it by the area, and takes the square root. Okay. There is a whole field of study called landscape ecology that uses landscape metrics a lot. There's a tool that was created by, I don't actually know the researcher who created it, but now it's maintained and developed by the U.S. government, and called FragStats, and it basically will take a bunch of polygons that might represent landscapes for different habitat types, and determine calculate landscape metrics. In other words, the compactness and the shape and the area, the perimeter, and will help you quantify those shapes. And you can look at the shape metrics through time. Is it becoming more fragmented? Are the shapes becoming longer and thinner? Things like that. All right, so now we're going to get back into spatial pattern and look at different ways of quantifying spatial pattern with polygons. And we're first going to talk about the kind of like the ones that are like the average nearest neighbor. That one is a simple, straightforward, easy to do in a GIS. That's not a lot of complicated math, right? The hypothesis test, coming up with the test statistic, is a little bit of math. So now, specifically with areas, one of the methods that we can do is called contact numbers. Contact numbers, what it does is it looks at the number of areas that share a common boundary with each area. So it basically is a measure of adjacency. And this isn't spatial autocorrelation. This is, well, it kind of is, but it's kind of telling us more about it's telling us more about the boundaries themselves. Okay? For example, look at the boundaries here in Michigan. See how they're mostly squares. Sometimes they even share just a common point. That doesn't happen with the United States. Think about the United States in terms of the East Coast versus the Western United States. Western United States, the shapes are much more regular, and there are less common boundaries than there are on the East Coast. What states share the most boundaries with other states?
Tennessee and Missouri.
Yeah, Tennessee and Missouri. Those are both east of the Mississippi. Well, Missouri is right on the Mississippi, right? I guess not really east, but they're both eastern half of the United States. In the West, there are less common boundaries. So you can use contact numbers to run a test to see if a pattern is more regular or if the actual pattern of the boundaries is less regular. In other words, the boundary patterns almost seem random. Okay. So here is the contact numbers for the U.S. 48 states. Here's the percentage of English counties. We're not really familiar with English counties, but we have a very similar mean value. If the boundaries were created through an independent random process, we would expect to have a mean number of 6 with the same number of observations. And so we can determine that they're not created randomly. Fragmentation. Yeah, that slide actually should have been up here. Okay. All right, so now let's get back into spatial autocorrelation, because this is what we are going to be talking about and calculating here in a second. Okay, so I think we covered that pretty well. So like I was trying to get at earlier, the first step in doing area pattern analysis is to kind of do a qualitative, is to actually look at a choropleth map. We take our data, we map it, we decide, hey, is it looking like it's clustered? Is it looking like it's random, or is it looking dispersed? And you look for a pattern, and as it is with any hypothesis test, you come up with a thing. This pattern that we saw with obesity here, we think that perhaps there is some clustering. We can even start to think of why. Why might that be? Well, it could be related to poverty, because these areas are certainly poorer areas. But do they tend to be clustered? And that's what we get to answer here. Okay. All right, so the first one that we're going to talk about is the one that I already calculated. That's Moran's I index. So Moran was a geographer that created this index. And the index really isn't like, really isn't much different. So Moran's I is basically the correlation coefficient. So I mean, it's good to create. I wasn't like trying to downplay. I didn't really do anything for it. But Moran's index is basically the same formula for the correlation coefficient. So if we have a positive value, that means that we have positive spatial autocorrelation. Negative value means that we have negative spatial autocorrelation. Anything that's around 0 means that it's random. Random spatial autocorrelation. There is a significance test. That's what this is showing the output of. That's what this is. This is actually the significance test for Moran's index right there. And so it is a z-score. If the z-score is above 1.96, we're getting into less than a 10% chance that it was a spatial pattern that occurred at random. And then same with the negative. So this just says Moran's I can be interpreted as a correlation between those variables. Another way to say what this is it's the variable, in this case prime, and this is the lag of prime, okay? The lag of x. So prime, lag of prime, or prime and its neighbor. That's what we're doing with. Yeah, and there's different ways. The way that's actually calculated in ArcGIS is it's the average of the neighbors. Now, it could be the spatially weighted average of the neighbors. Okay. It's not just the pairs. It could be just the pairs, but it's usually the average of everything that's considered a neighbor. And it could be the weighted average, in other words, weighted by distance. And that's how we got into talking about the network analyst stuff before, so I won't go down that tangent again. Okay. So the slope is the line of best fit. We'll talk about this a little bit more next week. We'll talk about regression more. Oops, sorry, I didn't turn my phone down. Let me do that. Okay. Hold on. All right, sorry. All right, so there's the Puerto Rico population density. That's the same, almost the exact same thing we showed before. All right, so Elvis asked a great question earlier and said, is there some sort of map I can get with this? Because we're geographers and we like to make maps, right? So no, with just the spatial autocorrelation, just that's what this one, by the way, Moran's I is what's created when you run this tool right here, spatial autocorrelation, right? So there is a way to run other analyses that look at local autocorrelation that's happening in the local areas. Hotspots are where the high values cluster together. The cold spots are where low values go together. The global Moran's I can't distinguish those. It's just giving you one number for the entire area. Okay, you can't tell if they're hot spots, cold spots, or both. It's just telling you that number. oftentimes it's good, it's useful to do these. And so here's a statistic, the Geddes Ord general global G statistic. It does distinguish between hot spots and cold spots. Basically, it's looking at the residual values of these areas, not the residual values, that's the distance from the thing, but it's basically looking at the highs and the low areas and mapping those for you, okay? So in those areas where there's lots of high values clustering, or if there's low values clustering, the way to look at this is that the statistic is interpreted relative to the expected value. In other words, it's relative to the trend line. So let's go ahead and run that for obesity. That is right here, the high-low clustering. So I'm going to run this for the county health rankings. I'm going to choose obesity as the field. And I'm going to generate my report. Let's do, I'll just keep it inverse distance.
Is this a trend of the high and low? Just telling you what expected based on the data that we see.
Yeah.
What next?
Actually, this is one step toward. This one actually doesn't output a map either, but it's getting closer to a map because this one is this one's basically telling you if it was significant because there were lots of high clusters or because there were lots of low clusters. So here is the high-low clustering report, and it shows you that. So the range here is not. So you would run the global Moran's I first to determine if there's clustering, and if there's clustering, you might wonder: are the high clusters more significant, or the low clusters are more significant, or is it just that that have a mix of both? In other words, are the clusters themselves clustered more in the high area, the low area, or right in between? Okay, still no map to produce. This one is saying that high clusters are more clustered, or the high clusters are more of a significant effect. They have more. The spatial process is creating more high clusters than it is low clusters. And it's significant. So that's what the, yeah. So,
Is the significance of the high clusters more than the significance of the low clusters? Is there more high cluster count than low
yes,
clusters?
that's what it's telling you. Is that there is a pretty big low cluster right here. Like right there, maybe up there, but what's driving the fact that this is a clustered map is the high clusters, not the low clusters. Is what that's saying. Is that there are the higher clusters are more significant than the lower clusters. So that's what this this analysis here is. The map's going to be the next one we talk about. Yeah.
Can you choose two colors, black and white? Would that make a difference overall? You got a map, you got 5 different applications. Can you change it to 2? Make one black and one white?
Sure, I can change the classification. How about 3? Let's see what 3 looks like. So look a little bit better. So get high, medium, low. In other words, yellow is, or I could just do this. Something lighter than that. There we go. So it's the dark blue areas are the most obese counties. The yellow are the least obese counties, and the green are the counties in the middle. Does that make sense? Percent obese.
So in the middle and the county that I had, they're more closely related than just the ones that are matched.
Yeah. All right. So this is the calculation for general G. We're not really going to talk about this too much, but what this is saying, I mean, it is using the weights, so basically, if nearby x values are both large, the numerator and the top will be large. If they are both small, the numerator and the top will be small. And so we're adding them all up, multiplying them by those weights. We just decided to do inverse distance, right? I think that's the way we ran it. And then we divide that by the total number. And so if you wind up with more hot spots, your number will be higher positive. If you wind up with more cold spots, you wind up with more negative values. And so then it'll tell you how significant it is, basically. So it's not really a tool for measuring autocorrelation, spatial autocorrelation. It is for determining if your clusters are more negative or more positive clusters. Okay, so it doesn't make any sense to run the high-low clustering if your data wasn't clustered. So if it was random or if it was dispersed, don't run it. If it was clustered and you want to know whether or not highs tend to cluster more or the lows tend to cluster more. So like, let's say we were asking, hey, in city A, do people of income levels, do they tend to cluster with other people that have similar income levels? Right? That'd be a valid question. So we could run that for New York. In New York, we find out that yes, there's significant clusters of income. That's what we'd run the global Moran's eye. We might run it for Los Angeles. We might run it for a few other cities. Find out if it was always significant in all those places. But then we might be further interested as to whether or not, let's say it ended up significant in all those places. We might be further interested to know whether or not the clustering was more significant if the clustering was more significant in low areas. In other words, do low-income people cluster more than the high-income people cluster, or vice versa? And we don't have to be. It doesn't have to be income. We could look at race. We could look at educational attainment. We could even, do it again. We could try to find some environmental variable. We could look at certain species and whether they tend to cluster in certain areas, not cluster in others. We have a way to measure that.
But there would be, if one wants to like each other, then there would be a positive cluster rather than a negative one. They are both clusters, but one more related to positive and it's more of a like.
In every data set, you're going to have some clustering, right? Like, unless it's total like made up data, you're going to see some clustering.
Right.
But yeah, I mean, this one's hard to tell. It's hard to tell whether or not it's the high values or the low values that cluster more, because there are some areas out here that cluster more. I mean, they cluster in the lows. But what this is telling you is there's more high clusters. And you can kind of see that. I mean, especially if we were to just look at neighboring pairs, there's a lot more neighboring pairs out here. And that's more simply a function of the fact that we're using counties, and counties are bigger out here than they are out here.
Right.
But we were using distance, so that should be negated a little bit. from the two data sets. Okay. All right. I promised I'd show you maps. So these maps are sometimes referred to as local indicators of spatial association, and these tools they calculate a statistic for each point or polygon. They can actually run on points too. If they're run on points, you obviously can't use contiguity. You would use distance. But so each unit, each polygon or point, it gets a number based on the values that it shares a neighbor with. So we're going to get a map that says how different it is from its neighbor. Okay. So here's just this is literature. Literacy. This is literacy in China. Okay. Each polygon is mapped. This is literacy in China. This is obese people in the United States. Percent obese in the United States. Same type of map. This is just different colors. Okay. This is the output of a local indicator of spatial association, and it's showing you the areas where there are high values next to other high values, or low values next to high values. That's what this is. This one is low values next to other low values, and then these other ones are just not significant. In other words, their neighbors are different, but they're not that different from each other. So this is showing you where the kind of the exceptional values are that are a lot different. Okay. So let's talk about what this actually means here and how it gets derived. Okay. So that's really the same map there. Okay. This is how it gets derived. Think about that scatter plot originally that had illiteracy and the lag of illiteracy in this case. In other words, the neighboring illiteracy. So if it appears in this quadrant, in other words, if that relationship appears over here, it's low, low. Okay? But it has to be far over here. And again, if it appears in this quadrant, it's high, high. In other words, it itself is high and it's surrounded by high. But it has to be out here. Anything that's kind of close to the middle here, it appears white on the map. In other words, it's not significantly different from its neighbors. Okay. And again, this is low-high, meaning it's a low value near a high value. And this is high-low, meaning that it's a high value, but it's near a bunch of low values. So that's actually, yeah, that's low-low. So I don't know if there is a high-low. Yeah, there's no high-low example on this map. But let's see if we do that same analysis on our data set, if we can do that. So this one is under mapping clusters. And this is the hotspot analysis, this one that I've just talked about. So this is a common tool to use. We're going to do county health rankings, we're going to do obesity, and we'll use inverse distance because we've been using that so much, and then run this. All right. So what we see here, we finally have an output. Okay, and we actually have a gradation of values here. So here we've just got, we've got 2 values. Here we've got 6 values. But we have the same sort of thing where we have the highs that are clustering with other highs and the lows that are clustering with other lows.
That 99% confidence is saying that it's for sure that those are cold spots. That 99% confidence means that this is very accurate. That reading on there on the side of the map where it says cold spot, 99% confidence.
Yeah, actually, cluster analysis. Sorry. This one is actually the one that I was discussing in the lecture. So here we'll do first distance weighted on the feature class. Yeah. All right.
The highest value has a higher level of confidence than the ones in the white. The white has no significance.
Right. So this is actually the one that I was just discussing here. Moran's local Moran's eye is what this is called. See, local Moran's eye. This is it. So here, the high clusters are saying, okay, these are high values nearby other high values, and the low high clusters are low values near other high values. We see any in Mississippi? In other words, these two counties are significantly lower obesity than the nearby counties. So that might be kind of interesting as to why those are different. Right? Well, those are two of the Jackson counties, right? Look at the Florida Gulf Coast here.
Yeah, that's the coast here. So they significantly the next thing is that are blue areas high up.
Yep. So these highs, those are like obese people that live nearby not so obese people. So these are like inland California, it looks like. This is like way out in the West Desert in Utah, and actually right here in the southeast portion of Wyoming. And you got a few clusters up there. Okay. Now let's see if we change this to be just neighbors, contiguity. I'm going to do edges and corners. It's not done yet. I'm pretty sure if I do this, it shows up a few more counties in Mississippi, including our own. Nope. But it did change the map a bit. There's actually less clusters because now we're looking at just edges rather than a distance. What if I do inverse distance squared?
Might that map be like, we covered it earlier, I don't know exactly what it's called, but it's like really misleading because, say for example, like on the right side where you have a little tiny county, there may be actually more people that are in that county than a larger county to the left, but because of the scale, it makes it look like there's more people because we've got a larger red spot, but there might actually be less people.
Well, yeah, the amount of people in each county's.
Would that be something you would weight it by?
Because these are, yeah, I mean, you could do that. Like, you could, I mean, this is just using percent. Right. So.
Comparison of quads, we talk about the quads, they're tied up in the quads, so the center games. We got another picture, they have one on the outer edge of it, so you might get the meaning of the picture.
I can't really hear you.
I was talking about the quads, when you show the quads picture. And
this one?
Compare one, yeah, when you compare one with the quad going tightly in the corners, in the middle, four cells together, and then you showed another picture, it was the same four squares, but they was pushed outward, and it's hard to make a distinction on there because they the same count, but it's different. When they spread it out, the same amount in each square versus.
This is kind of weird, right? Like, look at this. And that's almost, I mean, that follows the boundary between Georgia and Alabama. Like, why is Georgia in the Alabama in the high cluster and Georgia isn't? Like, that's kind of interesting. What's that? Like just because you cross over into Alabama, all of a sudden, let's see if that pattern. There is kind of a pattern there, right between those two states. Now I don't know if it's like a reporting difference in the two states or something, And then there's another, like this is actually like North Carolina. The North Carolina border is like right here. It's kind of weird. I think it actually does go all the way over to there. So it's interesting that we've got a North Carolina, Tennessee boundary a little bit. Anyway.
Well, they got more reporting rate, as you were saying, they probably don't get any data.
Yeah, I mean there could always be data issues.
The standards in obesity for those states might be totally different.
Yeah, I mean I think this is federal data. The idea is that it's supposed to be the same, but you never know. The point here is with that that Moran scatter plot is that you're in one of these quadrants. The area in the middle is what shows up white, and if you're in the a quadrant, you're answering this question. Basically, if you're in either of the corners, in other words, the darkest, this is the red, the dark red, this is the dark blue. You're saying that those areas you're similar to your neighbors. In other words, you're low, your neighbors are low. That's down here in this quadrant. You're high and your neighbors are high, significantly high. You're up there. And then if you're of the lighter blue color or the lighter red color, then you're different. You're different than your neighbors. So that's what... it's actually opposite of what I said. Darker is this way, lighter's that way. Red's up here, blue's down here. So the dark reds are I'm different than my neighbors. Dark blue is I'm different than my neighbors. Light blue means I'm the same as my neighbors and we're both low. Light red means we're the same as my neighbors and we're both high. It also outputs this histogram that you can open. This shows you the distribution of the percent obese. Here's a few other examples. This is showing income. I gave this example before. This is just the choropleth map of income, and this is the high-low clustering map of income. You can see that with this particular data set, there are very few low-high and high-low. So there's mostly high-high and low-low, and then there's a couple of instances where you've got a low income in the middle of this high income area. You got a high income in the middle of this low income area. But it looks a lot different than the smoking data set that we just did. Don't have as many of those in between values.
So you're saying that the picture you just showed a minute ago is how people actually live or where people actually work?
This is the city of Denver, and this is income mapped using this tool right here. This local cluster and outlier analysis, local Moran's eye.
Okay.
Yep. Okay, so I already actually ran this last one that we're going to talk about, the local Getty's 4G statistic. This one does it basically shows how high, it basically shows how significant high clusters are and how significant low clusters are. And so remember when we ran the general G statistic, and it said that the high clusters were more significant. So on this map, it's saying that there's more high statistics. It looks like there's just as many, but think not area-wise, but the strength of the pattern, because these are smaller units. There's a lot more of those smaller units there, and there's a lot more clusters. There's a cluster here, there's a cluster here, there's a cluster here, there's a cluster here, there's a cluster down here, there's a cluster up here. Here there's several clusters, but maybe they don't have as many. I'm not exactly sure why, But that's one reason why it's important to run the analysis here. So here's the output for, well, that's not the output for that. So that's this one right here, the hotspot analysis. Yes, what?
The strength of the cluster is defined by the color, and so that's why you're saying that the cluster pattern for high is stronger than the cluster pattern for blue.
Right.
Which is how.
Yep, that's exactly right. There's where I ran it. Okay. So this should create the same as that. All right, so that's the this only shows, again, this is only a tool that you run if you know you have clustering. So this tool right here, the local Moran's I, you can run no matter what. It's still only going to show you those clusters that exist, but the get a sort statistic shows you your high and your low clusters. It highlights those. So here's just an example of different outputs you could get using these different tools. So here's Getty's run 2 different times. Okay, one with using 1 as a distance and one with using 2 as a distance. Here's Getty's with a half, 0.5 as a distance. And that looks pretty similar to the high-low clustering. I mean, sorry, not high-low. This is high-low clustering. This is called high-low clustering. That was pretty similar to Lisa, the Moran's I, but you don't get these, you know, these that tell you about the diagonals as well. You get those values. This one and this one.
You get more nuance. Yeah.
Right. You get high, low, then the highs mixed with the lows, and the lows mixed with the highs with this. Whereas you're only going to get the highs and the lows here. And they're going to tell you how significant they are. So another important thing that this graph shows is that as you increase that distance threshold, typically you're going to see larger clusters. All right. So, last thing we're going to do, and then we'll take a break. Let's look at this story map. So, this was a story map that they created over a year ago because I had this last time I taught the course. But here we are looking at average traffic incidences in space and time. So, they're looking at, I kind of had a test question like this, right? Except for I had words. They actually created a tessellated surface, and they were looking at traffic incidents over time. And so they created a tessellated surface, and they calculated. So here's all the accidents that happened. Okay, this is along the Space Coast. Titusville is kind of near Cape Canaveral. Okay. So they created that, and then they did a hotspot analysis. But they did a hotspot analysis for each year. So once in 2000, I think the first year was 2010, 2011, 2012, 2013. So first they had the points, they aggregated the points into hexagons. We covered how to do that in class. They aggregated the points into hexagons, and then they created one for each, like kind of like we did with tornadoes, but they did year by year instead of month by month. Okay. So that's what they have here. And so what this legend is telling you is that, oh, and then after they did the thing that was like the tornadoes, they ran a hotspot analysis on it. And so what the red spots mean, the little hexagons with a dark red spot in the middle, that's a new hotspot. In other words, It wasn't a hotspot at the start of the study, but it became a hotspot later in the study. I'm not exactly sure how they made the cutoff, but in other words, it's an emerging new hotspot. Okay. The dark, the kind of dark pink color right here, those are areas that were always hotspots, or at least mostly hotspots. The reds were in some years those were hotspots of the pattern. Some years they were hotspots, some years they weren't. And then finally in this case, the blues and the light blues, these are the opposite. Okay. So here's another way to look at it. So they call these space-time clusters. So here it is looking through. This is the clusters looking through time. In other words, in the past there weren't a lot of accidents. It wasn't a hotspot for accidents, but now all of a sudden this is becoming a hotspot for accidents. Okay, this was actually a cold spot for accidents. In other words, accidents rarely happened here, and now they're happening with some frequency, but they're still not a hotspot. In other words, it's not a cluster.
Is a net space in time in a distance in time?
So this is a map. This is like you're looking at a side view. This is the same map as this, but now this is straight down. This is a side view. The side view is time. So the oldest times are at the bottom of the stack, and the top of the stack is the most recent time period. Does that make sense?
Yes.
Here, that's a good way to look at it. So new hotspot is emerging, consecutive hotspots, sporadic hotspots. All right, so you could create a map like this. The link for this is posted. You could create a map like this for the tornadoes now, if you really wanted to. Now, one of the things that they have done, this is a new tool. That story map was actually created before these tools were inside of ARC GIS, but now there's actually a whole new toolbox that they just put in a year ago, less than a year ago, that does, it's called the Space-Time Pattern Mining Tools. And what this does is it creates that tool that we just, it does it for you. So you can do emerging hotspots or local outlier analysis or time series clustering. So you can look at things through both space and time. So we're not actually going to run this in the lab, but you could start experimenting with that. You could use the tornado data if you wanted to. So you could bring up the tornado data. The workflow here is that you actually have to create a space-time cube first. So basically that's the same as running spatial join for all the different time periods you want to do. And then once you have that data set, you can run your hotspot analysis on that space-time cube.
Is the output of that on a map or just on an area to view? Is that a
yeah, it's almost what we it's almost exactly like what that story map presented. So click on this and question mark it. It's going to take your data, like let's say all these represented accidents or tornadoes in our case. Then it's going to create a cube like this. In fact, here. Add data. So we got our tornado points data. And turn off all this other stuff. Okay. So let's say we wanted to make a space-time cube with the tornado data. I don't think it's going to make that interesting of a map, but let's do it anyway. because I don't know that tornadoes are changing much through time, but maybe they are. So we've got our tornado points, and we're going to create our space-time cube. I'll just put it right here. I'll just call it tornado space-time cube, or space-time cube.
What's the time deal? What's that? Like 20 years, 30 years?
Well, you have to have, in order for this to work, you have to have a field that is of type date time. So I've got that right here. See that? So that field that I created called DT. If I go look at the fields, I would look at just the field properties. I could get to it right here. See how that DT field is? It's a date field. You have to have that. If you don't have that, it won't work. I'm just going to close this up. Okay. All right. So I'm choosing the date time field, and the template cube will allow you to basically create the exact same cube size dimensions that you already created for another project, but I haven't done it yet. The time step interval, I'm going to do 1. No, I'm going to do 10. I'm going to do 2 years. How many years is it since 1950? I think I should do 5 years.
60, 70.
Here you could say I want to start at a certain time period, okay, or end at a certain time period. I'm just going to let it pick the very last one, so it's going to go 5 years back from the very last one. If I wanted to choose a specific reference time as my last time period, then I could. So I think the very first one is 1/3/1950. So if I choose start time, it'll go from 1/3/1950 till 1/3/1955. Okay. Or if I chose reference time, then I'm going to say, okay, I want to choose I want to choose 1950. Okay, so I'm going to go from, that'll make more sense, right? So I'm going to go from January 1st all the way till January 1st, 1950 to January 1st, 1955, and then to January 1st, 1960, and so on. Okay. You can choose what aggregation shape you like. I love hexagons. That's my favorite. So I'm going to choose hexagons. And then I have to choose how big the hexagons are. And so I'm going to say that they're going to be, this is the whole United States. So I'm going to say they're 100 miles. I wonder if that's too long. And then this is like kind of like with the spatial join, you have to choose what field you're going to choose. And so I'm going to choose the magnitude field. Now the magnitude has the negative ones in it. I'm going to choose the loss field. And I'm going to sum the loss. So in other words, I'm getting a summary of the loss. I'm going to sum up all the losses and look at tornado loss. Of course, loss through the years is just, yeah. I think I should just use magnitude. What is this STN, I wonder? What I really need is, with join count I can just add it. So I'm just going to call this TN. So save. And then what I'm going to do is calculate field. One, run it. So now I just created a field with a bunch of ones in it. Sometimes you have to do that. And then I guess I lost all my other information. Tornado points. What did I call it? Tornadoes. Space-time cube. Save. Time field. Date time. Template cube. Nope. 5 years. This is going to be almost identical if I just say start time, fishnet, distance interval, 100 miles. The United States is like 3,000 miles across. I think I'm going to do 200 miles, just so it doesn't take forever. Okay, then the field is going to be the sum of that TN field I just created, which is just everything's a 1. So I'll get just the count of tornadoes. Execute it. Oh. Fill empty bins with zeros. In other words, no tornadoes happened, then that's fine. They'll be zeros. Now we'll run it. All right. So it created the space-time cube, and that space-time cube exists on disk. It's this file. ArcGIS doesn't even open that by default. There's no way to visualize that until I run some analysis on it. So now I go back to here and say I want to look at the local outlier analysis, time series clustering. Time series clustering will just be, are they high, low? Okay, so count gets created by default. So both of these should be the same. Characteristic of instance, value. All right. So those are clustering through time. Not exactly sure.
200 miles.
Yeah, I should have done something smaller, right? Maybe. Here's emerging hotspot analysis. This will probably be a little bit more interesting. Analysis variable, sum of tornadoes. I just didn't want to take it forever to run. Yeah, look fine. Okay, so here's the result of the analysis. Okay. So the areas right here in the center are supposedly intensifying hotspots. In other words, we're getting more tornadoes in those areas, whereas these areas out here, those are diminishing cold hotspots. So over time, less tornadoes. And these are persistent cold spots. In other words, they never have tornadoes. There's always close to 0. Okay. What is this one? Oscillating hotspots. Sometimes it's hot, sometimes it's cold through time. Each 5-year period, we have sometimes hot, sometimes cold in those areas. And then these are consecutive hotspots, meaning that they're almost always hot in a 5-year period. So it is kind of interesting to look at. It's a different way to think about it. You're thinking about it through time, but what you're seeing is the result of running that hotspot analysis, the spatial autocorrelation analysis. But you're seeing different symbols through time. I'm not sure if you can view it at an angle like you could with the other data, but that is what we see there.
Why did it come out as squares and hexagons?
Did I say hexagons? I think I did hexagons the first time, but I was in a rush the second time through, and I didn't choose hexagons.
Oh, maybe converting something else.
What?
That's the United States map?
That is the United States map.
Oh, I see. So if you made it smaller, you could have saw it as of the United States, like smaller, less than 200.
Yeah. 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 Why don't we take a break and I can rerun it real quick and I'll make them smaller. I was worried it would take like 10 minutes to run. So let's take a short break. and then I'll just rerun it and show you the results. But then we'll talk about the lab. So it's 226 right now. So let's come back in 15 minutes. So that'll be 240.